In this video, we're going to take a look at spherical coordinates and its parametric surface formulation. Okay, so in the previous video, we chose the simple example of cylindrical coordinates. That was a pretty easy extension of polar coordinates in the xy plane where we added on a z variable, right? And the reason we're drawing these cylinders is because cylindrical coordinates was a description of every point in space and thinking of it as being on a cylinder of some radius, okay? So that was cylindrical coordinates. But without knowing all the formulas yet, we can also view every point in XYZ space. You can think of it having a description, every point here, P, being on some sort of sphere of a different radius. So if I keep expanding these spheres, at some point we're going to have a sphere that is of the right radius to intersect this point P. And then you'll notice that this point P maybe is going to be over here, and so it's on a sphere of some radius, right? But if you're on that sphere, it may be at an angle down here in the xy plane. You have to go over this much and then come up on the sphere of this angle, right? If you're over here at the point P, you'll have to come over an angle this way and then come up on the sphere in this direction. So if we're going to be looking at points being on spheres, there are two angles to be dealing with if we're working on a sphere. In a cylinder, to get to a point P, all you needed to know was what radius you were on, and then you had to go around the cylinder in one angle and then just come straight up z. So there's only one angle in cylindrical coordinates, and you had one height variable and you had one radius variable. So in spherical, if we're working in spherical coordinates, trying to describe a point P as being on a sphere of some radius, you're going to have one radius and two angles. Those two angles are given the names theta and phi. Okay, and let's see if we can figure out what theta and phi represent. Theta and phi, over here I have the parametric description. I'm going to write down this function, r of u comma v. I'm going to write down, this is a slightly more complicated function, cosine of u, sine of v, sine of theta, sine of, I don't have u's and v's. Okay, let me write this in terms of the thetas. So there are two variables, r of theta and phi. Here are two variables, and you have cosine of theta, sine of phi, sine of theta, sine of phi, and then the third entry is just cosine of phi. Okay, and let's see if we can figure out what's going on with this plot just using parametric plot 3D. We are in 3D, and you're in 3D, but you have two variables. In this case, we're calling the variables theta and phi, using Greek letters because that usually indicates some sort of angular variable. Okay, so if you take a look at this, I've made up this function, parametric plot. I've typed exactly what I've written here. And because there are two variables, you can choose those two variables to be whatever value you want. And I usually pick pi, some form of pi, which indicates we're dealing with angles. So here theta is going from 0 to pi over 2, and phi is going from 0 to pi. And if you take a look here, that is giving us this little part, this little shape. Okay? You'll recognize this as a sphere if I let theta go from 0 to 2 times pi. Okay? And phi, let's let phi go from 0 to pi over 2. Okay? Now, there's the top half of the sphere. And if you let phi go from 0 to pi, we will actually have a sphere. Now, we should be very careful here. This is actually only a parametric plot 3D. It's in 3D with 2 variables. But this is only the surface plot style. If you take a look at directive and you give this some opacity, let's say 0.5, you'll notice that this is only the shell of a sphere, right? So if you let phi go maybe from maybe up to just 3, you'll see that maybe about 2.5. You can see that we're only dealing with the shell of the sphere, right? So you only can describe the shell of a sphere with a vector valued function in 2 variables. So notice here that the radius, the number in front of here, the radius is 1. Right? So if I wanted to plot a sphere of a different radius, I could put 2 here, put a 2 here, and then put a 2 in front of the cosine of phi. And this would change the radius of the sphere, but still it would only be a shell of the sphere. So the radius changed to 2. Okay. Right. So this is what we did in cylindrical coordinates. We introduced the idea of how do you plot parametrically one cylinder, and then we get to the spherical coordinates or cylindrical coordinates by adding in a changing radius. Okay. So here we can see that if we change the radius, we'll get a sphere of a different radius, getting bigger out this way. And let's still figure out what the angles theta and phi do. I think you'll notice here that if phi goes from 0 to, let's just say 1, there are 2 angles in this problem. Phi goes from 0 to 1. Okay. Notice that you're only getting the little you're only getting the little top part of this sphere. Okay. So the bigger phi gets, that angle phi is being measured from the North Pole down to the bottom of the sphere this way. So as phi gets bigger, 3, we're getting more of the sphere measured from the top. So phi is the angle measured from the North Pole down to the xy plane. All right? And theta, if we let theta only go from 0 to pi, theta is our angle around the sphere this way, measured from the x-axis over to the y-axis. So the x-axis over to the y-axis, that would be your angle theta. And if you plot this, okay, something happened there. Let me get rid of these plots. And I changed theta to only 0 to pi. And there you go, you have only half of the sphere in the xy plane. Okay? So this is going to be our route into spherical coordinates. Spherical coordinates, instead of having only 2 variables, you have your spherical coordinates. The spherical coordinates are going to be the variables rho, theta, and phi. And the transform involved there will be rho, theta, phi, which is a transform from rho, theta, phi space to xyz space. And you would write rho cosine theta sine phi, just by putting a variable radius in front of here. So rho sine phi, rho sine theta sine phi. Sorry, the pen's not working very well. And then rho cosine phi. And the idea here is that if you choose like rho is equal to 1, theta is equal to 0, phi is equal to pi over 2, right? And you want to figure out what's going on in the XYZ space. What I mean by that is we have three new variables, rho, theta, and phi. And if you pick this particular point, rho is equal to 1, theta is equal to 0, phi is equal to pi over 2, this point, okay, this point, let's say in a cube over here, this point, and you want to figure out what point that corresponds to in XYZ space, right? So there's going to be some point over here that's on some sphere and is at some angle theta and is at some angle phi measured down from the z-axis and is on some radius rho, some sphere, okay, and that would be your point Q. Which point Q will we be at if we use these rho, theta, and phi variables? Well, you'll be at the point 1 cosine of 0 sine of pi over 2, and sine of pi over 2 is 1, cosine of 0 is 0, so you're at an x value of 0. Y, you'll be at 1 sine of sine of theta, you'll be sine of 0 sine pi over 2, and that will be 0. And then z, you'll be at a value of z is rho cosine theta, so you'll be at 1 times the cosine of pi over 2, and that is also 0. So if you want to look at this point, you will be at the point x equal to 0. Whoa, hold on just 1 second. Because 0, 0, 0 would be this point, but I'm at, wait, cosine of pi over 2. That's 0. I think I've got my x value wrong. Hold on a second. Rho cosine theta sine phi. Cosine of 0 is 1. Sine of pi over 2 is also 1. So I'm sorry, this should be a 1. So you will be at the point 1 in the x direction, 0 in the y direction, 0 in the z. So this point here does correspond to being on a sphere of radius 1. You are at an angle theta. You have not gone any angle in the xy direction from the x-axis to the y-axis. We've gone no angle that way. And we have come pi over 2 down from the z-axis down pi over 2 degrees. And that puts us at this point here. So the reason we are looking at spherical coordinates is because what if we had a region that we wanted to integrate over, do a triple integral? Right? What if we needed to find the mass of a part of the sphere that was only in the, so this is the part of the sphere, in the first octant. Okay? And, you know, this is solid, right? Because it's a 3D region. And what if we had some density function on that, and it was our job to figure out how much this little wedge of a solid, this wedge of a sphere, what is its mass if we have a density function of rho. So you would probably have to compute some triple integral over this region R of this density function, and we would have to do a dv integral. And we wouldn't want to do that integral because it could be very difficult in Cartesian or rectangular coordinates, so you'd want to be able to transform this region. And it would be simple to transform this region because your theta variable would go from 0 to pi over 2. The phi variable would go from 0 to pi over 2. And then your radius variable rho would go from 0 to 1. So if you let theta, phi, and rho be all the values between 0 and pi over 2, 0, pi over 2, and 0 and 1, that would be that would be a cube from 0 to 1, 0 to pi over 2, and pi over 2 in the phi direction, the theta direction, and then the rho direction. You would have a cube that looked like this. That cube would transform under the spherical coordinates transform up here to this part of the solid, this solid. And then we would be then doing a triple integral over rho, theta, and phi, but we would need a compensation term. And we will deal with these kinds of integrals over the next couple days. And so that's just how I'm viewing spherical and cylindrical coordinates and their relationship to these parametric plots. And when you plot parametrically, you can only plot parametrically with two variables at once. And so from there, it's pretty easy to self-adjust the other variable, in this case the rho variable, to figure out what's going on. Okay, so that ends this video.